Good afternoon, Doctor. We are Group 6. We will be presenting our group assignment, which focused on fast Fourier transform FFT. So my name is Kan Heng and my team member is Lin Jingyi, Lin Xin, and Mok Wing Hua. So fast Fourier transform is an efficiency algorithm to compute discrete Fourier transform DFT. It used to convert the signal from the time domain to the frequency domains, which allow us to analyze the frequency components, magnitude phase, and also the dominant frequencies. Because of this, FFT was widely used in signal processing applications. However, the traditional DFT has a major limitations. Its computational complexity is very high. For an n-point signal, DFT requires n-square multiplications, which making it slow and inefficient, especially for large signals or real-time applications such as audio processing and communication system. So in order to solve the problem, FFT has improved the efficiency by reducing the redundant calculations. It breaks the DFT into smaller parts and reduce computations. As a result, the complexity is reduced from order n squared to order n log n. For larger n, FFT is much faster than DFT and is preferred method for practical signal processing.
Alright, now I'd like to explain a little bit about the main working principle of FFT. So the main principle is that FFT is a method that splits DFT into even and odd indices of time domain. And the split odd and even indices are called n/2 point DFT, and the simplified equation becomes as follows. So usually for FFT, we will split them into odd and even indices. Then we only split them into 2. However, we can further split them into 4 and use the bit reversal method to be able to sort the input depending on our requirements. So the butterfly structure in FFT is the smallest split of FFT, which operates with a pair of odd and even samples. So the output is the sum and the difference of both samples. So here is an example of a even higher point FFT where we need to use more butterfly structures with a 4-point FFT. So here we will have 4 different values of transformation basis. So I'd like to talk about some of the applications of FFT in signal processing. So the first application is spectrum analysis, followed by noise removal, and lastly, image and video compression.
Good day everyone, my name is Lin Jingyi and now I will explain about the example question. From this question, we are given an input of a discrete time signal which is xn equal to 1, -1, 1, -1. To find its DTFT, we use this x omega formula. Since the signal has only 4 samples which is from 0 to 3, we will next substitute this 0 to 3 and the magnitude of input signal inside this formula to get the equation. And for the omega equal to 0.25 pi, we will then substitute this 0.255 back to this equation to get the answer of 1 plus j 0.4142. Finally, to calculate the DTFT magnitude response, we need to calculate for the absolute value and hence we will get the final answer of 1.0824. Next, we want to repeat the question 8 using 8-point DFT by first finding the k value for omega equal to 0.25 pi. First and foremost, we will get the formula of omega which is equal to 2 pi k over n from the DFT formula above where n equal to 8. Next, we will rearrange the equation to get the k value by substituting the omega with 0.25 pi and n equal to 8. Next, to calculate the DFT magnitude response, we need to substitute all the k value and number of samples inside the equation to get the final answer of 1.0824, and this answer is proved that to be same as the question A before. After that, we will compute the 4-point FFT xk of the input signal xn using the butterfly diagram, then compute the complexity of the 4-point FFT. So from the butterfly diagram below, we will first separate the signal into even index sample and odd index sample. The even sample are x0 and x2, while the odd sample are x1 and x3. We then perform the first butterfly stage. For the even part, we calculate x even 0 which is equal to 2 and x even 1 which is equal to 0. For the odd part, we get x odd 0 equal to -2 and x odd 1 equal to 0. Next, we will combine this result using the Twiddle factors that has been discussed before. After the second butterfly stage, we obtain the final FFT output which is xk equal to 0040. Finally, the computational complexity of a 4-point FFT is n log 2n which is equal to 8 with the n equal to 4.
Good day everyone, my name is Lin Xin. Today I'll briefly explain why the radius to fast Fourier transform or FFT is a fast and efficient way to compute the discrete Fourier transform. First, radius to FFT uses a divide and conquer approach. It breaks an n-point DFT into smaller n over 2 points DFTs, which significantly reduce the number of calculations. Second, FFT expresses the symmetry of Twiddle factors. Since these complex exponential values repeat in a regular pattern, FFT avoids unnecessary repeated computation, thereby improving speed. Third, FFT uses a recursive butterfly structure where the same simple add and subtract operation is reused across multiple stages. This makes the algorithm efficient and easy to implement. As a result, FFT reduced computational complexity from O(n)² in DFT to O(n log 2n, making real-time signal processing possible. One limitation of radius to FFT is that the signal length must be a power of 2. If not, zero padding is required, which may slightly increase processing time. In conclusion, radius to FFT is a powerful and widely used algorithm that enables fast frequency domain analysis in many signal processing applications. That's all from our group. Thank you.